So, does anybody? All right, today we're going to talk about the ACC. Does anybody have a sense of why we talked about the MOC last time and why we're talking about the ACC now? Why, out of all the remaining things in the world to choose to talk about after we're done with gyres and waves, which are like fundamental dynamical pieces, would we be picking these two?
I mean, they have something to do with climate change.
Exactly. So these are the key parts of the system that have to do with climate change. We're heading towards wrapping up on a discussion of climate change and some of the pieces. And those of you who are in my IPCC class have seen a lot of the bits of the climate change. So this is a lighter part of the climate change, but we're trying to link the ocean side of that to this piece. So last time we talked about the MOC, and the discussion focused on whether it was whether it's stable, whether it's variable, whether it's crashing. And so we were talking about using the stream function to quantify its strength. We talked about rapid. We talked about the bits and pieces of that story. Today we're going to do the same thing, but we're going to do it for the ACC, which is also, well, the ACC itself is current that we talked about that has low pressure on the Antarctic side and high pressure on the other. It's a geostrophic current, but there's a secondary circulation, an overturning circulation across the Southern Ocean. And that brings up water water at one location comes up, interacts with the surface, and then becomes either intermediate water heading back north or Antarctic bottom water and heads back north. And in both of those branches, we think that is where all of, so what absorbs more gas, cold water or warm water? Cold. So if you want to make a really strong seltzer, I finally figured out that if you do this with seltzer, this is the way I learned this. I have a little seltzer maker at home. And so if you I was thinking that you'd make it with just like regular tap water and you add ice. No, you want to get really cold water. And then also the CO2 doesn't go in immediately. You actually want to let it sit for a minute after you've done the injection to equalize the gas. All right, so that's how you make seltzer. But for the ocean side, colder water exposed to the atmosphere for a while will saturate, and it will saturate with more when the colder it is. So which water masses then do you think were recently at the surface, will long be at the bottom, that would absorb a lot of carbon dioxide while they're up there? Which water masses have we talked about that have that kind of properties and are also in cold places?
In AMOC, the ones that's going down.
Exactly. The North Atlantic deep water that forms in the Labrador and Erminger Seas at the surface and goes down and comes back in the middle. And then the Antarctic bottom water, which is the other deep one that forms near Antarctica and goes in. So the Southern Ocean overturning and the AMOC are both critical parts of taking anthropogenic carbon and taking it down into the deep ocean where it doesn't interact with the atmosphere for centuries to millennia. So carbon into the ocean, one of the biggest places that it goes is around the Southern Ocean, and then also heat going into the ocean. A lot of it goes into the Southern Ocean. So the Southern Ocean changes are really, really big in the same way that the potential shutdown of the North Atlantic was a big part of the climate change question. Whether or not the Southern Ocean will continue to uptake carbon, or whether it'll stop at some point and be like, I've had enough, now I'm not taking any more. There's a big part for how much of the carbon that we emit hangs around in the atmosphere. If we emit a bunch, but it all goes into the Southern Ocean, then it does acidify the ocean, but it doesn't lead to global warming. If it doesn't go into the ocean, it leads to global warming. Does that make sense to everybody? And right now, the concentration of carbon dioxide in the atmosphere is going up so fast that it's definitely going into the ocean, because the direction of carbon dioxide exchange has to do with the difference in the partial pressure in the ocean and the partial pressure in the atmosphere. So if we change the atmospheric part, then if we raise in the atmosphere, it tends to go into the ocean. So even if the temperature and salinity and everything in the ocean stays fixed, it'll go that way. But if you hold those two and you warm up the ocean, it'll go the other way. because the ocean, the colder it is, the more CO2 it takes. So there's a competing effect where the increasing concentration in the atmosphere is driving more into the ocean, and the warming of the ocean is tending to drive it out. So what exactly how that balance gets struck is why this is an interesting and complicated problem. That's the sort of biogeochemical side. We're going to talk about the physics side, which is just what are the currents, where is it going, what do we want to think about, how could we look at them in echo. Okay. Oh. We already talked about this yesterday. We actually did a good job of getting through everything for the, we did a good job of getting through all this stuff yesterday. We closed on that funny energy budget last time. So, okay. Is the overturning circulation likely to change? This actually, so this is a little last bit that we didn't get to yesterday about the MOC before we move on to the Southern Ocean. So the overturning is highly nonlinear because there's like an advection part, there's a buoyancy part. If you think of the temperature and salinity equation, they've got all those velocity times salinity and velocity times temperature pieces, and those are going to affect the density, which is then coming back into the momentum equation and changing the velocities. So we've got two active components, the velocities and the density, the active tracers, the one that affect density in product. So everybody is nonlinear in this game. So the energetics constrain, we had to mix up after we sank down, but they're in a strongly nonlinear system like this. Is it possible that you have more than one solution for the same forcing? So let me think for a second. So how weird is, well, maybe I'm not explaining it well enough because it is very weird. If you have a light switch and you flip it on, the lights come on, you flip it off, the lights go off. If you have two light switches and they both switch the same thing, you have a couple of different choices. They could either be both up or one down, one up, one down, the other one up, whatever. There are a couple of different settings. If you can imagine a case where you have to flip a switch and then go flip the other switch before you get back to it, back to where you were. Or to switch the condition of lights, you could have multiple things have to happen. You also could imagine a situation maybe that it was sequence dependent. Like if you did this first, then that, then you went the other way, you wouldn't get back to where you were by just reversing your direction. That is a terrible example, but there are processes which has something that's called hysteresis. So the idea of hysteresis is when you go one way, if you try and reverse yourself, you can't go back the same path you came. And so systems that have hysteresis, kind of closely related to that, will have multiple solutions at the same forcing level. So suppose I say I'm cooling at this rate, and this is my temperature today. Let me draw a picture. Here's my overturning strength, and here's my temperature, say. So suppose I'm here, and we go warmer, and the AMOC gets weaker. So heading in this direction, we go to here. And then we say, oh no, we've ruined our plan, let's suck all the carbon out and use geoengineering, and we go back this way. We might not go back on the same path. In fact, we might go on a path like this, and then only after we've gone way past where we started out do we get back to the same kind of level. So this is a hysteresis loop. As I'm changing my parameter, I have a path-dependent level of my other variables. And now notice that for this temperature, one in the middle, say our present temperature, there are two different values. So this is not a function. This is there are multiple solutions for the same forcing. That is a characteristic of a nonlinear system. A quadratic equation has multiple solutions for the same coefficients. It's the same kind of thing, but it's in the dynamical systems version of it. So for the AMOC, this is what Hank Stommel, once again, he came up with a toy model for the AMOC and showed that it actually has multiple solutions. There are 3 solutions to his toy model, 2 steady ones and 1 unsteady one, and they have exactly this kind of behavior where you go one direction and you shut down and then you come back and you have to go past where you were before you get back to the same solution branch. Does that make sense a little bit? So we don't know whether this is true in the real world. It's true in that toy model. It's true in some kind of intermediate complexity circulation models. It's not so clear that it's true in full high resolution eddy turbulent models or not. And we really have little idea whether it's true in the real world. So this Stommel box model is the toy model. It's a nice example of multiple solutions for the same forcing. But we can wonder whether the real world's like that. So here's the echo estimate. So estimated values of the AMOC. There's a big shutdown here at the end. So that one looks like it's shutting down. Hold on. What are we seeing? This is latitude. So here's latitude. So this is the overturning strength as a function of latitude. So overturning, and then it tails off when you get up here. So this is where the AMOC starts, and then it goes all the way to the southern hemisphere like that. And there's some variability. And then this one is meters. So this is the depth of that maximum. So this is sort of the core of this overturning stream function. So it's at, say, 1,000 meters, circulation towards the north on top, circulation towards the south on the bottom of that strength is what this is showing. Yeah, that figure. This is the stream function. So remember the AMOC looks like, and stream function looks kind of like this. And here's the North Pole, here's the equator, and it heads out that way. So what's being mapped in the top is the magnitude. So basically the maximum at any depth, and what's being mapped in the bottom is the depth of the maximum. So yeah, so this is, and then the error bars are showing you the time variability. So it's giving you a sense of how strong it is, how much it varies. So it's 15 spherodraps plus or minus 4 or something like that as the maximum. And the depth is 1,000 meters plus or minus quite a bit at the equator, and a little bit deeper in the southern hemisphere. And that's sort of the central axis of this overturn. Does that make sense?
Yeah, except that when we were talking about the western boundary currents, then my impression was that it's more that the stronger stream function would be at the surface and along the bottom boundary, and an interior would be much weaker. So in that sense, I would expect that I don't understand how that configures what you're talking about.
Yeah, so you're thinking of the stronger velocity, which is the compression of the stream function, the compaction. This is the maximum. So remember the stream function increases, reaches a maximum, decreases, in order to have a northward flow above, like this, flow above, southward flow below. So it's the integral of this. So the maximum is in the middle, and then it goes back down.
It's because it's a gradient.
Yeah, so if I took the vertical derivative of that thing, then I would get the flow speed. And if the flow speed is really, really surface intensified, that would mean that I would have a stream function that looked like this, where all the gradient was up top. But I could have one that goes like this for a while and then still goes like this, and then in the middle it turns around, which is kind of what, so there's a surface bit, but the maximum is still somewhere mid-depth, which is the location where you reverse direction. Yeah, John?
This is just a general question. So we talked about the Gulf Stream and the gyres as a western boundary current.
Yeah.
And then it seems that we're also talking about the Gulf Stream with relation to AMOC.
Yeah.
So is it a part of both, or?
Yes.
Okay.
So kind of in that whole Stommel and Ahrens, like there are western boundary currents that help you move stuff around when you have a source and sink, and in order to stay in the vorticity balance. like one simple way to think of the western boundary current is whenever you need to move something meridionally and you don't have the winds to do it with the sphere drip relation, just stick it in a western boundary current and then it can go wherever it needs to go. So flows from sources to sinks of that particular water mass will tend to go in the western boundary current if they can't go in a sphere drip relation. If the sphere drip relation is going the wrong direction or whatever, or you just need to add some extra volume to do the overturning on top of the gyre.
Okay, so both forcings are driving the Gulf Stream?
Yeah, so the Gulf Stream is like a return flow for the wind-driven part and a return flow for the sinking, but it's combining them both together. And so, and you can, they don't quite add up to half and half because actually it's kind of double counted in the top part of this, and it's kind of double counted this way because there is some overturning the subtropical cells involved in the gyre, and there is some east-west variability implied because this is not like a uniform flow across the basin. It's actually in western, deep western and surface boundary currents with some circulation, recirculations built in. So we're averaging in the zonal direction here, or integrating in the zonal direction to make this simple to think about. And when we thought about the gyre, we would integrate top to bottom in order to make it simple to think about, but actually the flow is a complex kind of spiraling pattern. And there's a beautiful paper which we didn't read, but anyway, if you look in a model, it's actually a space-filling curve, the trajectory of a single parcel. So it's not only is it like looped together, but it's actually chaotic, the trajectories that go through it. And it's chaotic even in the steady case. Steady chaos is a weird thing. But it basically means that if you release a parcel, it'll eventually color in the whole world ocean by going around and around and around on this very complex, strange attractor. Okay, maybe that's too much. Anyway, okay, that's a cool thing, but it's not directly what we want to talk about today. Okay, this is the Stommel box model that I was saying. This is the toy model. And what it is there's a northern, this is like a polar ocean, and an equatorial ocean. And this is hooked to a reservoir, which is cold, so minus whatever values. This is hooked to a reservoir that's warm. And you can have salt forcing and you can have temperature forcing. And there's only one temperature allowed at the pole because you have a little stir bar. And there's only one temperature allowed at the equator because you have a stir bar. In the real world, that whole question about like, do tides drive this, whatever, is all represented by this little stir bar. So there's an infinite amount of energy to keep them well mixed in this toy model. So that question of whether the tides were the hindering factor on the return flow is not a question in this. And then the second part of this is you specify the potential to overturn, which is basically whichever one is denser sinks down and gets sucked along a little pipe at a rate that's proportional to the density difference. And then the return flow just spills back from one into the other on the top. So if you drain out this pipe, this one would go down, and then you get some spill from the other one as you fill it up. Does that make sense to everybody? So this is his conceptual toy model. And it turns out that you can write down these equations exactly for this toy model, and you can solve them. They're a nonlinear fourth order coupled ODE, but some of the equations drop out as linear subsets, and those are easy to solve. And then there's a nonlinear second order equation that's kind of nonlinear third order equation that's left. So I want to show a little bit about how that works. So this is a graphical way of solving, looking for steady state solutions of that nonlinear ordinary differential equation. And without getting into too much detail, the time rate of change would be 0 for the system when this line intersects one of these other lines. These three are different forcing conditions. So A is like strong forcing, B is intermediate, and C is weak forcing. So the difference in the temperatures and salinities between those two boxes is what I mean by strong, weak, and none. So now you can get a sense of what I meant by multiple solutions. So in the C case, there's only one solution that would be steady. You go to this point on, and that's the intersection, that's the only one you could have, and it has an overturning strength which is negative, which actually is the opposite of the way that our present system goes. It doesn't sink at the north because it is cold, it sinks at the equator because it's salty. And so it goes backwards. So that's what this negative positive means. So in the C case, that's the only steady solution. It doesn't matter where if you started with some greater overturning, it would collapse on, it would have a trend onto that. If you started some lesser one, it would grow until it got to that. In the the B case, this one is just barely missing, so there's only one solution over here. And that's a slightly positive overturning strength, which is the only one that's available in that forcing scenario. So it only intersects right there. But now look at the A case. There's an intersection here, there's an intersection here, and there's an intersection here. So if you start out nearby either this one or this one, they are both stable solutions. So you would go from a nearby value onto this one or a nearby value onto this one. It turns out if you start out nearby this one, you would actually go away from it. So this one's an unstable solution. So there are two stable solutions and one unstable solution. So the unstable solutions, you run away from it if you're not right on it, and the stable solutions, you fall into them if you're not right on it. So you can imagine in this A case, it depends on where you start out. If I start out near this one, I'm going to stay near this one. And if I start out near this one, I'm going to stay on this one. Does that make sense to everybody? Okay, now here's the mind-bending part. Imagine we change the forcing in time so that we are oscillating between the C case and the B case through the A case. So if I start out down here and we crank down towards the C case, I would just slide over there because those are nearby. Everybody on board with that? If I start out here, I would start, heading up this peak as the peak comes down, but eventually the peak is going to cross that line and disappear, and then I don't have that solution anymore. So what will I do?
Collapse the other one.
I'd zoom down to this one. So there would be an abrupt climate change at the moment that that peak crossed the line in that part of forcing space. And now, here's what I mean about hysteresis. So now, suppose we start cranking the forcing back up again, and we get back to the A case. But we started out over here. Now where are we? We're going to be at this one. So on the way down, we were riding on this stable fixed point, but as soon as it disappeared, we collapsed onto this one. And then when we ride back up, we're going to stay on this one. We're not going to get back to this one. We won't get back to that one until it's risen so much that that solution slides all the way over here and then disappears, and then we collapse onto that one. So if we have this as point, let me get my labels right. This is A upper, A lower, this is C, and this is B. So if we start on the upper value of A, and then we lower it down, when it collapses, we jump down to C over here. And then as we increase, we go through the other branch of A, this branch of A, until we collapse back onto the high value of B. And so hysteresis in this system is related to the fact that there are multiple solutions on that intermediate branch, and that the other branches are either or. Does that sort of make sense a little bit? So this is a typical thing that happens in nonlinear dynamical systems all the time. This is a really weird one, and that Stommel did this like 30 years before people were talking about this in dynamical systems. So classic Stommel, he was like, oh yeah, I'll just do it like this. It makes sense to me like this. Anyway, so this kind of thing is now called there's a blue sky bifurcation when this breaks through there, which is something you might have heard in applied math. And then this is this kind of thing is called hysteresis, and there are multiple equilibria in the system. Oh, and now I'm doing it the haline mode. Sorry, now I'm putting labels on it. The thermal mode, whatever. And then I have a little toy model. If you want to play with this, I actually have this all coded in a time-dependent way on my webpage. You can go grab it on the Models tab. And this is just an example of showing sinusoidal and time perturbations of the forcing. And so if you start out here on this, sorry, this is insane notation. This is an attempt to draw these little guys. So one loop, the red loop, actually does undergo the hysteresis, where it's jumping from one branch to the other. If you have smaller perturbations, you actually can stay on just one branch or the other branch without jumping across. And so if our real world is like this, and we have reason to think that it is because, as one of you very nicely did in your paper, we have seen the AMOC shut down in paleo history before. So it is possible, we think, to jump from that branch to that branch under sufficiently strong freshwater forcing. If that happens, we're not going to get the AMOC back until we are colder than our present climate. Not back to our present climate. We might actually have to go significantly farther to get it restarted. Does this sort of make sense? So there's a possibility in this toy model, possibly in the real world, of shutting down and starting back up. In more complicated models, it looks like the restart of the AMOC is kind of natural. Like you can shut it down, and then like a couple hundred years later, it comes back on its own, even without changing the forcing. So this is maybe not the right dynamical system to explain that behavior. But this is something that Stommel said, and then Wally Broker got all excited about, and then he convinced everybody in paleoclimate that this was the way to explain all climate change at all times. And then later he changed his mind, thought it was a bad idea, and he convinced him that this was a terrible thing to think about. But anyway, Wally was very good at getting lots of people excited about ideas. This is a really cool idea, and it has hung around as one of the interesting aspects of climate change, that's ocean-driven climate change. Does that make sense to people? Okay. So, will it actually shut down? So this is the part that we actually already talked about before with the Harry Bryden data, whether it's not shutting down. Okay. So that's one possible way that the oceans can play a big role in climate change. If the AMOC shuts down, what do we expect to happen? The Gulf Stream's going to slow down. The amount of heat delivered from the equator to the neighborhood of Western Europe is going to would change, which if the overall planet is warming, that might not mean that it cools off in Europe, but it might mean that it warms up slower. What about sea level rise? What does the Gulf Stream have in sea surface height signature? It's on one side it's low, on the other side it's high, and then it's like this. So if I reduce the transport of the Gulf Stream by shutting down the AMOC part, what happens? It's going to go like this, right? So right now it's like this because it is not the same on both sides because there's a net northward transport. But if I turn off the AMOC part, it's going to go like this. So where in the world am I going to see sea level rise? Rhode Island, exactly. Rhode Island, Eastern Canada, all along the North Atlantic seaboard, western side, we would expect to see sea level rise. So, and it's a lot. It's order half a meter. Because across the Gulf Stream is about 1 meter now, and you're talking about reducing basically half of it. Yeah.
Isn't it possible that the Gulf Stream will just be associated with a gyre, and the gyre will intensify to compensate for the lack of overturning?
In terms of the heat transport, yes, that's actually pretty likely. Or even faster than that, so if the AMOC shuts down and then it stops moving heat northward, then it starts getting cold on one end and warm on the other, which now makes the gyre more efficient because it's now, the Gulf Stream is essentially getting warmer and the sphere drip flow is getting colder. So that's one response. The other response is that top of atmosphere radiative balance we talked about last time, you basically can't miss that for long by much because the atmosphere warms up. So if you shut down the Gulf Stream, the atmosphere is going to take over really quickly to build it up, which is not as good as it sounds, because how does the atmosphere transfer heat across, from the northern side of the Hadley cell to the polar front? What? Storms. So if you shut down the AMOC, the storminess should go way up, which is not what you want to have happen. It will keep Europe warm, but it'll be warm because there'll be a lot of hurricanes, which isn't necessarily what you want. So, that makes sense to everybody? These are some of the pieces put together. In real models, the response is a blend of all those things. So it's not totally compensated. All those changes happen in different amounts, and it's sort of model dependent what the answer is.
Yeah.
Yeah.
I have one more follow-up question. So you're kind of assuming that the AMOC is the only way to transport heat, but isn't another possibility that would just be less efficient, and then the ocean would somehow have a new system to transport heat, because it's not in equilibrium if it doesn't transport heat.
No, and the AMOC is not the only way. The gyre is also transporting heat. And so what I was saying is if you shut down the AMOC part, you're going to start cooling the northern side of the gyre and heating the southern side. So the gyre will get more efficient, because now it'll be transporting warmer and colder. So a lot of it would be compensated just by the gyre. And the atmosphere also is compensating, driving these warm, tropical cyclones up into the cold spot. Tropical cyclones into Labrador. Anyway. Which would be exciting. Maybe too exciting. Okay, the ACC. So some of these ideas actually are going to come back in the ACC. So here's our crazy picture. So the ACC it's the spoke, or no, it's the hub of the hub and spoke diagram of the ocean. It's the thing that connects all the other basins. And the Antarctic bottom water is formed right around the Antarctica and then sinks to the bottom and fills out into the other basins. Antarctic bottom water is the most common water type. Most of the water in the world is Antarctic bottom water, even though it comes from a very small place, because it's so dense that it just slowly fills up from the bottom until it mixes up. But there are these other intermediate waters and Pacific deep waters that are coming up, and North Atlantic deep waters coming up, and then there's I don't know what so we would like to understand how that part of the branches work. So collapsing it to look just from the side, so this is the whole world, and this is looking at the global overturning, which is kind of crazy, but anyway. So this is the Atlantic and Pacific and Indian. So the North Atlantic deep water is the only overturning in the north side, so that's what's making this part. And then there's mixing up to a kind of shallower part. There's a surface cell which goes like this and becomes North Atlantic deep water. And then here's the Antarctic bottom water filling in everywhere else. So when we look at the ACC, this part, which is underneath the westerly winds, we see that there's kind of an upwelling in the intermediate depths, a surface, and a deep cell. So there's kind of a closed deep cell and a closed surface cell as the two parts of what that global overturning stream function looks like. So both of them have a branch in the ACC, and so somewhere here in the middle of the ACC, we're getting water that's coming to the surface and either choosing to go this way or choosing to go that way. So we want to get a sense of how that happens and where. So here's the ACC from above. These two lines indicate two fronts that kind of pinch where the fast flow is in between those two fronts. And then here we're looking from the side this is the south side on these three. This is temperature, salinity, and oxygen. So, okay, now we know how to read oxygen. How do I read that figure? Or this one too? Where are the water masses there? This is 34.7, this is 34, this is 34.6.
And the
boundary, there is the 34.7.
Yeah. So we're going up like this, bringing up this salty North Atlantic water,
And then it splits.
and then it splits and goes down this way or that way. And then oxygen, these are 180, 200 up here, so these are bright colors. And then, oxygen is more complicated in this case. And then there's lower oxygen over here, and lower oxygen over here. So where's the downwelling part of this guy? There's one other key weird thing about the reading the oxygen that makes this really hard. Where's this branch, the descending branch on this figure?
It's the yellow.
It's the bright yellow. So this stuff came up to the surface, got reoxygenated, and then sunk back down as mode water, and there it is, or becoming intermediate water. Why don't we see bright yellows over here? That water also was recently at the surface.
There's no nutrients.
there's a different flow rate, there's consumption, and then there's also a problem that like what surface conditions you saw means that oxygen isn't a perfect tracer. Like it depends on what temperature it was at as to how much oxygen it got. So this is not an easy one to read. But the temperature, the fresh water, the lower oxygen, this is water that's been down there a long time, but we know from other things that is being refed slowly from this trickle down that side. So oxygen is not conserved over a long time, it is conserved for a while. So this is the younger it which is going down quickly. This is really relatively old water, even though it's it was on a circuit that's going that way. So it's a little bit about the rate of the overturning as well, and the volume into which it's going, and also things like sediment consumption. Okay. So in geostrophic terms, we know there's a pressure difference across the current, and so there's a big wide current. That's part of our story. Okay. So, is this ACC geostrophic? If these are the pressure contours? Could be, right? I mean, it's low pressure on one side and high on the other. That's the right direction to drive it. Is it wind driven? Sort of. Kind of. How? In what sense could it be wind driven? Or maybe what's our closest analog of a wind-driven system that looks like this? So can it be a sphere gyre? That's a good question. Let's skip ahead to is this the right one? Yes. Suppose we have a flow this direction. Oh, suppose we have, hold on. Sorry. It's not a western boundary current. It can't be a western boundary current. In fact, it's sort of like an eastern boundary current, because which way does the wind blow? The wind blows this way, so which way does the Ekman flow go? North. So this is like a low pressure left behind by the Ekman evacuation, and then you get a flow along that. So it looks more like an eastern boundary current than a western boundary current. It's not a return flow for a sphere drip. Why can't we have the sphere drip relation? So when we have the sphere drip relation, what happens to the sea surface height? It increases and increases and increases and increases. So here, if there's a curl of the wind stress, which there is, so that we were moving water that way, we'd have an increase, come around, come around, increase. We need to, in order to have a sphere drip balance, we need to have a western boundary current to keep us from just running off to infinity. So it can't be wind driven like that. It can't be sphere drip driven. What about flow in this direction? So we were just talking about, oh, there's an upwelling and then it turns over, goes back that way. Can that flow be geostrophic?
The net flow can't be geostrophic because that requires pressure difference, but you can just integrate around the whole boundary to get no net pressure change.
Exactly. This is sort of a different way of saying the same thing I just said with the sphere drip relation case. So if we have a meridional flow, this is what geostrophy would look like. There'd be a pressure gradient in the x direction, but I could always integrate this around the x direction or around 0 to 2 pi going all the way around the Earth. And that would say that my flow, the integral, my net meridional flow would be 1 over rho naught times the pressure evaluated at 2 pi minus the pressure evaluated at 0, which is 0. So there can be no net geostrophic flow across the ACC because of this. Net is really important. And this is the math doing the same game for the sphere drip relation, but basically it comes down to where you're looking at dA to dx's or d pressure dx, and you go around and it comes out to be 0. If you go look in the real world, there actually is a sill and Drake Passage. So this is at the southern tip of South America. So below the sill, you have a little gyre. There's a gyre sitting down below. And so you can have geostrophic flow over here and western boundary current leaning up against the sill in the deep water. But up in that open part is where we can't close that way. And we might just have all of our meridional flow happening down below the sill. That's one possible situation. But there's something more interesting that happens in the ACC, which is really kind of cool. This is some insane Vallis figure having to do with this setup. We're going to skip that. Okay, let's look. Suppose we have this. Let's look at what would happen to the density surfaces. So it's cold on one side, hot on the other. So what do you think the density surfaces would look like? We actually just looked at them. You can go back and look at them. Oops. I mean, this is temperature and salinity, but what does the density look like? It's cold on this side, it's warm on this side, and they're kind of sloping in between. Sloping across. And which way does the Ekman transport go? North, because it's coming from the west to the left, so it's going north. So the Ekman transport is tending to push push the colder stuff on top of the warmer stuff. So it's trying to steepen those isopycnals. It's trying to go like this. Does that make sense to everybody? And so, here's our sill. We could have a flow that goes like this. Here's the Ekman transport, and it goes up until it gets totally steep, and if it overturns, it would just start mixing. So we can just draw them as vertical. So it's cold on one side, warm on the other. There's the Ekman cell that's going around and around. It can return at depth below the cell because there it can lean against the wall. You have a deep western boundary current down here, and then at the surface it has an Ekman. So that's one possible set of solutions. Does that look like the observations that we just looked at? Very vaguely. I mean, it's cold on one side, it's warm on the other. It's more of that temperature difference at the surface than at depth. Those pieces look a lot like the observations. Let's go back and look at the observations again. So, oops. Let's go one too far. Cold, warm, bigger gradient at the surface than at depth. Down here below the topography, it looks kind of flatter. And maybe that's not so crazy, but these aren't vertical. Why do you think they're not? Any guesses?
Well, there's transport coming in with the like AMOC and Pacific.
Right. So this part of the story is kind of like, it's a little bit like that upward part and that upper cell, a little, but we don't have a lower cell here somehow. And also, these guys are really vertical. And that last one said that they weren't vertical. So let me ask this a different way. If I have water that is light here and dense there at the same level, there's a buoyancy difference, and so there's a thermal wind, which is awesome because that's the ACC. It is in thermal wind balance with that. But I could gain energy by tipping over. I could put the light stuff on top of the dense stuff and get some energy out. Could sink all the, if I just sorted from the light stuff to the dense stuff, I'd end up with a lower energy state. So geostrophy is really weird in this setting. We know that we can't have a net overturning in the mean geostrophy, so the geostrophy would love to get at that energy, but it's not allowed to because it's a reentrant channel. And the flow of the ACC itself is in the wrong direction to extract. It's going perpendicular. There is a way that we can extract that energy if we do it in a non-systematic way. So some parts of this could flow that way, and some parts of this could flow that way. So averaging over the whole current, we have no net transport of volume. But if the ones that are moving south are systematically warm, and the ones that are moving north are systematically cold, we would actually be transporting heat or transporting tracers, oxygen, salinity, whatever. So where's an example where we have that kind of systematic, we talked about this a couple different times, where we have a systematic sorting across a gradient by what kind of motion? Talked about it a little bit in Ekman. We talked about it a little bit in thermal diffusion. What kinds of processes would do that? We actually talked about it in the atmosphere. We just talked about it a minute ago in the atmosphere.
Do you mean like the sorting of like heat from the equator to the poles?
Yeah. So the sorting of heat from the equator to the poles. We can do it with gyres, we can do it with an overturning, but in the atmosphere we do it with the Hadley cell, and then outside of the Hadley cell what happens? Storms. Warm, moist air going one way, cold, dry air coming back to replace it. We could have an ocean analog of storms. We could have warm eddies going one way and cold eddies going the other way. And they would have no net volume transport because of that constraint on the geostrophic flow we just talked about, but they might have a net heat transport. And that's exactly what happens. So if you take a model that doesn't resolve eddies, you actually do get something quite like that with vertical isopycnals. The Ekman pumps and then it overturns and you get mixing. If you run a model that's eddy resolving, all those isopycnals just slump down because the eddies fight against this. The tipping of those isopycnals to vertical means there's a whole lot of energy there. The eddies grab that energy and push it back down partly. So the eddies are in some kind of balance. If you turn up the wind, the eddies actually get stronger. So to first order, what happens is that you can change the wind and you don't change the isopycnals at all. You just make more eddies. So this is something that's a big part of the conversation about how the Southern Ocean responds to climate change. In this kind of model, if you make the wind stronger, you get more mixing, more overturning, you put more carbon into the water column, and the ACC gets stronger. In this kind of model, you put more wind on, the eddies get stronger, and you don't get the same effect on carbon or warming. So this is one of the key places in the world where high resolution models differ from low resolution models, and we think it has a big effect on the climate sensitivity of the models themselves. If that makes sense. So to put it another way, so if we're looking now, this is along the ACC and this is vertical. What we're talking about is little eddies that might be a hot eddy, which would tend to have an anomalous flow that way, and a cold eddy where the isopycnals or isotherms are pushed upward. And if you just think about the geostrophic flow that goes along with these and the matching sea surface height variation, you would actually get those plus minuses like this. And if this is at the same height as it is over here, we know that all of those will cancel out to zero by the time you go all the way around. But because it's systematically sending cold stuff, it's drawn the other way, cold stuff going this way and hot stuff going that way, it's sorting across that front, the temperatures. So there's a heat transport and other tracers, like stuff that's surface-like, hotter, fresher, whatever the surface is going that way systematically. Stuff that's more bottom-like, colder, that whatever salinity that water is going that way systematically. So you're changing the gradients as you flow like that.
When you say that the warm eddies are going southward and the cold eddies are going northward, is that just because of the way that they're spinning, they move in a certain direction, or is that like the bottom is moving southward and the top is moving, like the surface is moving northward?
Oh, you mean these? So I'm saying this is a warm eddy because this isotherm is pushed down. And then if you do geostrophy on that, you figure out that the flow, because of this tilt, is actually in that direction. This one is a little bit weird because it's not in the right orientation for the ACC. Oh no, it is. It is. So this is a warm eddy. So if this stuff wanted to go that way, it would turn to the right. Am I doing that backwards? Oh no, this stuff would want to flow on top of that. This would go underneath that. So this goes this way, but then it gets deflected to the left. If you try and put this stuff, it gets deflected to the left, which is that way. So that's just essentially doing the thermal wind from these density anomalies.
Okay.
Which
So
way does it go?
Is it tracking with the flow that we were just talking about, with like the cold coming up below the warm?
Yes. So if we go back to this vision, the Ekman transport is this way. The eddies are supplying water in kind of opposition to the Ekman transport, moving hot stuff against the cold stuff. And so we'll see in a second how those different stream functions add up. That's where we're going. So this is the storm version of the same thing. This is like tropical air going north and then cold polar air going south. So when we get storms or high pressure systems, it's exactly the same kind of sorting where we can't have a net geostrophic flow through that because we go all the way around the Earth, but we can sort the temperature and humidity by having the storms systematically move one way when they're hot and warm, moist, and the other way when they're cold and dry. And so that's how the atmospheric meridional heat transport works across the subtropics, essentially, across the 40s and 50s of latitude. And, as usual, we can look at these eddies on satellites and what do they look like. So this is SST looking around the ACC from a satellite. And you can see there are all these little wiggles. And if you watch one in particular, the warm side is going one direction and the cold side is going the other direction. They're sorting themselves. It's not a great movie, but it's a little too low resolution to see exactly what's happening.
Why is there a white area?
Oh, that's sea ice. Yeah, this is ocean temperatures or where the sea ice is. All right. now we can get into a really subtle point of whether this is wind driven or not. Namely, what happens if I blow a wind on the surface of a current like that? I'm going to be making the current go faster, at least initially, right? We think of the eastern boundary current case, but actually this is a continual injection of momentum in the same direction as the wind from the atmosphere down into the ocean. So where does the momentum go? Well, it turns out this same pattern of out, in of eddies, together with these wrinkles, systematically pushes momentum downward. So it takes the wind-induced stress and balances it against the stress at the bottom of the ocean. And the stress on the intervening layers is carried down by those eddies. So one layer, the eddies are dragging on this layer, these eddies are dragging on the next layer, those eddies are dragging the next layer all the way down. So whatever stress you put into the surface gets transferred through from layer to layer to layer until it can be interacts with that sill and the bottom drag at the bottom. So the eddies are intrinsically part of the stress balance too. And now here's the funny part. If you go through all that math and figure out how much meridional transport do you need to make the stresses balance, it says that the overturning due to Ekman has to be exactly canceled by the net overturning due to the eddies. So in thickness. So I know that's a weird concept. Let me try and show you with pictures. So if you just map the overturning in like a little channel meant to map that, this is what the Ekman flow looks like. It goes up and then it comes down and it returns back. So this is the Ekman layer and then this is just a return flow for it. And if you seal off this wall and say balance the surface stress to the bottom stress with that downward eddy transport, this is what the eddy overturning circulation looks like. It tries to almost exactly cancel that out. It doesn't quite do it. There's a little residual. And it turns out that this is the one that actually moves the water around. Because you're trying to follow the Ekman, and then the eddies are pushing you back. You're trying to follow the Ekman, the eddies are pushing you back. And one of those has got to win. The intermediate one, the residual of those two, is the thing that wins. And that residual is what actually ends up transporting the water masses around. So it's, yeah. So when we look from the side, we might have cold, warm. Here's the Ekman transport going this way, trying to turn that way. Here's the eddy heat transport going that way, trying to turn the other way. And the residual looks like an intermediate depth upwelling, a lower cell, and an upper cell. So this is sort of a crazy set of really complicated dynamics to get us back to where we saw from the water masses at the beginning. The water mass, we could have said, the water masses are telling us this story, how do we explain it? And that's actually how this whole thing got discovered. The water masses said this, the Ekman said this, and those are clearly inconsistent. So it took a lot of work by a lot of people, primarily in Southampton and at MIT, to figure out that this part is the part that adds together with that story to give you this circulation. Does that make sense? So in echo, this part is parametrized, something called the Gent and McWilliams parametrization. And you can look at the net of the advective and diffusive fluxes and find this overturning stream function. I think actually the overturning stream functions might even be a diagnostic that's in the model. But anyway, this story is sitting there if you wanted to try and diagnose it for paper number 4. Okay, there's one last piece of the story, which is a little bit of algebra. So let's pause here and do some conceptual thinking before we look at the little bit of algebra, because I've said something that's very funny that should have made you very concerned, but probably didn't because I went fast. This is an MIT GCM run, but it's not echo. It's just the ACC channel. This is from Ryan Abernathy, from his PhD thesis. Yeah, you can recognize that he's got it's a very three-dimensional artistic layout. Yeah. What?
It's an awesome figure.
Yeah. I mean, it's just so clever. And he's got the wind stress in there and the heat flux all like beautifully laid out together. You don't need any words to understand what's going on, except you do have to know what the definitions of the stream functions are. But okay, so now to ask you one of the tricky problems. We said there could be no net meridional overturning. What is this then? How can you have a overturning stream function if you don't have a net meridional overturning?
It's not a geostrophic balance.
It is in geostrophic balance. It's not in net geostrophic balance. So it's a funny thing, which was kind of subtle in this figure. The net transport at a z level is canceling, positive, negative. But how much net transport is there in that layer following the thickness of the layer? Is it net in or net out? So I'm thinking of integrating the velocity from the surface down to that. Which way gets shortchanged if you do the integral over that layer?
Out, because it's a thinner.
Out, because it's thinner. So there is a non-trivial correlation of thickness perturbation and velocity perturbation. So this can be not equal to 0, even if v bar is equal to 0. So you can have a product that is transporting whatever kind of water is in that layer net northward, but doesn't actually transport any volume net northward. And then this next layer down has the same story. It has a different H prime field, but it still is thinner here, thicker here. So it has a different H prime, V prime. But there's that. So I can write down something that has the units of V bar, but is not equal to 0. So this is like the thickness weighted velocity, average velocity. Does that make sense? I take the velocity and I weight it based on the thickness of that layer. That's what this is. Everybody sort of following what that means? This is the thing that I integrate and get that eddy transport out of. So I do dx, dz of this, and that's what gives me the eddy stream function that's in that last figure. Yeah, so look, the h up top and the h in the bottom cancel for units. So this is, so if I do v dx dz, that would just give me my psi Ekman. That's the only overturning I have is the Ekman part. So this is the perturbation around that. This guy has no v bar because it's geostrophic, but it can have an h prime v prime net transfer. Does that sort of make a little sense? So this is one of the only times in this whole class that we have talked about cross correlations being non-zero. This is the term in the equation that we always throw away. This is the term where we say, we don't want everything to be nonlinear. It would be terrible if it was nonlinear. We couldn't possibly think about it. There's no explanation here that is not nonlinear for this term. So that transport by the eddies is fundamentally a nonlinear transport. So this is why this comes at the end of the class, even though this is maybe the most important part of the client, we've now got the MOC and this. Both of them are fundamentally nonlinear collapses. Both of them are the things that we think are maybe responsible for the biggest sensitivity to climate change. So we've got this huge nonlinearity in the real system when we think of how to think about climate change. Does that make sense to everybody? Why we've held this till the end, and also why we're only going subtly into detail. There is one part of the climate change story. We're going to talk about climate change for the remaining classes after today. We're going to talk about sea level, ocean acidification, and ocean warming, and how those are related over the next couple classes. There is one part of the story that is not horribly nonlinear, and we actually do have a handle on, which is the subtropical cells. If we warm the gyres up, they'll suck some water down and put it in those pipelines down in the subsurface where the subducted water is, coming along. We talked about how it goes down across the subtropical gyre and then comes up at the equator. That is actually the part of the ocean that is warming most now, because all that water, aside from the surface, this below the mixed layer, that's the water that's warming most, because it's most rapidly flushed out. That's the overturning cell that has the shortest time scale. So those waters are already the ones that are taking up most of the carbon and most of the heat, just because they're in contact. But we know that eventually those are going to actually overturn pretty soon, and then they'll be done. They'll just be in equilibrium. The deeper waters have longer time scales, so they will be lagging behind climate change, but North Atlantic deep water warming, Antarctic bottom water warming are underway, but they haven't had a flushing time scale since industrialization. So they're not warm yet. They're just going that way. Okay, everybody seems very confused. So maybe in a different, if I had not called this class Ocean Circulation and Climate, I used to just call this class Intro to Ocean Dynamics, and I did not do this part. I did not do the MOC, I did not do the ACC. And I did it just straight up because I thought just the dynamical concepts we can understand at the level of math and the level of analysis and the models we're using doesn't require us to go into this. But in order to make this link up to climate change, I thought that it was worth putting these pieces in. So do you guys think this is somewhat helpful? Just to have, at this level of detail, these are what people are talking about when they're talking about climate change in the ocean? Even though really, you have the tools, you know how to go take a model and do model analysis, and you could get a high resolution model that has all these eddies and do all this stuff. I have confidence in you now based on the pieces that you got that you could go into this, but this is kind of beyond what we're able to look at directly, easily in this class. So this is the kind of thing that I talk about in the GFD class, which I will teach next spring. So some of you might want to take that. Some of you will not be here. So that's that. All right, cool. Tuesday I won't be here. So we don't have class on Tuesday. And then Thursday we're talking about sea level rise. So the homeworks are coming Saturday, I think, for homework 4. And plans are coming shortly after that. And homework 4 is pretty broad. It could, paper 4 could be anything about waves. Could be surface gravity waves if you just want to mess around with those equations. Could be look for a different data stream about surface gravity waves, like buoy data from offshore of Narragansett or whatever. Could be SSH Hofmuller diagrams from ECHO. Could be MOC diagnosis, whether it's the North Atlantic deep water or the ACC overturning in ECHO. Those are definitely good pieces of the story. So it's among all these later topics, make your own. And it's really free form. We built up to the point where we could talk about western boundary currents. And that one was really pretty prescribed. Here's the homework, use it to do something. This one is back open again because now you know how to do this. So go for it. Find something interesting to think about. Cool? All right.